Yeah, and we have a lot of students presentations. So yeah. So for today, basically, I will tell that after, but in any case, I will moderate all the sessions today, and for tomorrow, I don't know. I can continue doing that basically because I'm responsible, so it's no problem.
Yeah.
Okay. So remember that we all have, I mean, all invited speakers have 45 minutes for their talk, including questions.
Yeah, I will perhaps talk for 35 minutes, and then we
Excellent.
could have
Yeah,
some
yeah.
discussion.
Yeah, me too, yeah.
Yeah, and unfortunately, I have a meeting after my talk, so I will miss your talk. I'm sorry about that.
Well,
but,
it's no, it's life. It's no problem.
I hope, yeah.
We all understand that people have other things to do. So. This is what is nice about Zoom. The only thing which is nice about Zoom is that we can really we can save some time.
Yeah.
So yeah, what about you, Jonas? Are you working from home as well?
No,
most of the time. No?
not anymore. But until November, until 1st of November, we had most of the things online and all teaching online. But now from 1st of November, we are teaching in classrooms, and we can have meetings on campus, and most of the things are back to normal.
I see. It's good.
Yeah.
Unfortunately, it's not our case at all.
No, not yet, at least.
Not yet. No.
Not yet. It will come.
Well, it will come
at some time,
sooner or later.
Yeah.
Yeah. Hello, Evelyn.
Hello.
Evelyn.
Do
can you hear us? Okay.
Yes, everything is okay. Do you hear me also?
Yes,
okay.
We can hear you and
Good.
we can see you.
Very good.
Very good, yeah. I think you are at home.
No.
Evelyn, no?
My
in the office? Ah, yeah.
Everything
good.
is well up to now. Everything is okay in France. We teach in France.
I know. Yes.
And we can go to work.
It's okay. I mean, it's okay in France. So I hope it will remain like that.
Remain, but I'm not sure.
Yeah.
We will see. Hi, Jonas. Hi, Frank.
Hi, Evelyn.
Hello. Good morning. Hi.
Hello, Manas. How are you?
Good morning. Hi.
Okay, so I think more and more people are connecting now, so I can start with a short introduction, and people will hopefully join us because it's 9:45. Yes, yeah. Anyway, so thank you very much for connecting and for participating in the conference. And I should say that, of course, most of us remember better times where we had these nanostructures for photonics conferences and schools in Peterhof. You have been there, and in a better time. I mean, with a nice weather, you know, and this is what I miss very much in this period of time is physical interactions and, you know, discussing with my colleagues and friends the scientific research, basically. And of course, we all miss traveling. But at the moment, situation, I mean, COVID situation in Russia in general and in St. Petersburg is not good at all. So originally, the conference was planned to be held in a mixed format where at least some Russian participants, depending on their view, could physically come to a New Peterhof hotel, but I have canceled that because the hotel is effectively closed, and it's very difficult to actually to come in. And therefore, even the Russian participants, including young scientists, will give their talks on Zoom. Therefore, I hope that the situation will change sooner or later, and we can meet again in Peterhof and enjoy the real conference. Okay, but what is important that in this time we are still able to work, and we are still able to communicate and collaborate using computers, of course, but it's better than nothing. And that's why I would like to welcome all the participants and really thank you very much. And with this, I think we can start. So a few things. So I will moderate all the sessions, at least today, but I think tomorrow as well. And what we have is 15 invited talks from different countries. And each invited speaker has 45 minutes for the talk, including questions. Then we have, I think, 27 students' presentations in the afternoon sessions, and they will all have 15 minutes for their talks, including questions, basically. That's the format. So we didn't organize any discussions or any, poster session, because I didn't know how to do that. So it's all going to be oral presentations. Yeah. Frank, do you want to add something as a co-organizer?
No, Vladimir, I think you have said everything. Of course, like you, I miss direct interactions, because obviously it's much easier to discuss, in particular, scientific matters face to face. Must say here also we miss meeting in Peterhof, which was a particularly nice place for us, but that's maybe a minor aspect of the COVID crisis. Yes, here everything is normal at the moment, but it might not be the case forever, because the number of cases seems to be increasing quite sharply again. So we'll see, but I think we all want to thank you for having organized this kind of replacement session of NSP to maintain the thread of these conferences, and we're kind of sure that the next one will be a physical meeting in Peterhof if you decide so, or in another nice place if you prefer, but we will all be waiting for this.
I think we will keep Peterhof. Yeah.
Well, I think that would be your choice, but it's your choice in the end.
Yeah. Thanks. Thank you, Frank. So yeah, okay. So let's wait for another about 10 minutes, and then at 10, Frank, you start. So I will introduce you, and then you will continue. Okay.
Okay.
I can see some students connecting. Very good. Very good. Yeah. Manas, how is the situation in Germany? Because I have seen that again the number of cases is sharply increasing, and particularly in Bavaria, I think.
It's rising really fast everywhere, especially in Saxony here. Mm-hmm. People have a different view in general. So,
but do you have any new, like restrictions introduced due to that?
I think this week they started with this, what they call the 2G rule, which is the ones who already had COVID or the vaccinated. Only these two groups can enter shops and events, but not the ones who are not vaccinated. Even if they have a test, this is not enough.
That's not enough. Mm-hmm.
You should have some antibodies developed.
Mm-hmm. I see.
But it's rising really fast. So Basically, even my son got it just yesterday. He was tested positive.
Oh.
And it started from his school on Friday. So many classmates got it. That's why I stayed home today. So, but
yes,
it would have happened sooner or later. I mean, it's everywhere, especially in schools. It's really bad.
Yeah, in schools, of course, it's very difficult to, I mean, to keep this social distance in schools. Yeah, that's clear. Yeah, it's the same here. Yes. Frank, maybe you will try to, I mean, to share your screen to check if it works for you.
Yes, I will try to share my screen. Maybe I can start trying to share my screen.
It was working. I mean, I checked that, but just in case.
Do you see it? Do you see it?
Yes, we can see it. Yes.
And now I'm trying to. Sorry, maybe I'm going to go back. Do you still see it?
Yes.
And do you see my pointer? Most important.
Yes.
Everything seems to work then.
Well, yes, provided that there is no thunderstorm here. I mean, for me, because I'm or storm. It happened once 2 weeks ago. We really had a terrible storm here, so the trees were falling, and I had no electricity in my new place for about 6 or 7 hours.
Yeah, we have storms here as well, but in 7 o'clock in November in Paris, storm is extremely unlikely.
No, November. It's a time for storms here. But at the moment, it seems quiet and sunny, so it should be okay. We'll see. Because I'm at the sea, you know. Right at the sea.
So it's still quite dark here. Just that's the outside of the building. So daylight is coming slowly.
Yeah, in my case, it's sunny.
Ah, much nicer.
So this is my new place. Okay, I think we can start. So, good morning, everyone, and welcome to the NSP 2021 conference, which is held via Zoom, unfortunately, but still welcome, and thank you very much for connecting. So we will start our first session, which is a theoretical session with a talk of Frank Glass from C2N and entitled Modeling VLS nanowire Growth at the Monolayer Level, Energetics, Kinetics, Statistics. Frank, the stage is yours.
Thank you, Vladimir. Can you still hear me?
Yes.
So I'm going to speak about vapor, liquid, solid growth of nanowires. And it's a choice system to study phase transitions in confined nanosize medium because the nanowire grows from atoms which are stored in a small liquid droplet. Of course, for us, it's important because what happens at the growth stage governs the properties of individual nanowires or heterostructures in nanowires or ensembles of nanowires. And the message of this talk will be that in such small systems, the size matters, the fact that we have small number of atoms matters, but also that we have features with different dimensionalities. We have volumes, for instance, the droplet and the nanowire. We have areas like the periphery of the droplet or the interface between the nanowire and the droplet, and we have lines bordering these. So I will illustrate this and in the case of a deep study of what happens when single monolayers grow in nanowires. And I will illustrate my talk with examples taken from 3,5 nanowires grown by molecular beam epitaxy, but some of the ideas are much more general. So first an introduction with basics of VLS growth. Then I will speak about the formation of a single monolayer, and I will show that there are 3 stages in the formation of each single monolayer. And then I will go to sequences of such monolayers, kinetics, statistics, and possibility of quasi-deterministic nanowire growth. We see what it means. So first, I thank the people with whom I've been working for about 15 years about nanowires. So my colleagues from C2N, Jean-Christophe Armand, Gilles Patriarche, Federico Panchera, Fabrice Heller. Special thanks to Professor Dubrovsky, with whom I had great pleasures to collaborate for about 15 years, and also to the various students and other people who worked on this. So I start with very simple ideas. So a few facts about nucleation, 2D nucleation from a large supersaturated liquid. So this will be our reference. So here we don't take into account the small size of the system, but our liquid is supersaturated, which means that there is a positive difference of chemical potential for a 3-5 pair between the liquid and the solid, supersaturation. And we can calculate the work of formation of an island, which contains I pair. So I transfer I 3-5 pairs from the liquid to the solid. So the supersaturation delta mu positive is favorable to this transfer, but of course there's a price to pay for it. Each time we create an island, we have to generate the edge of the island, which has a specific energy, which I will call gamma NL or gamma E. But here we have a first example of the differences of dimensionalities. The volume of the island scales, of course, with the number of pairs I that I have transferred. But the edge scales only typically with the square root of this number because it's an edge feature. So if we calculate the work of formation, we have a negative term, which is favorable to the formation of this island, which is simply the product of the number of pairs that I have transferred times the difference of chemical potential. But we have a term positive, which opposes the formation of the island, which scales as the square root of the number of pairs. So this gives the typical well-known nucleation curves. At the beginning, the positive term dominates, so it's not favorable to form the island. But because of fluctuation, we may reach this nucleation barrier at at which, of course, the derivative of this work of formation with respect to size is equal to 0. And then after this, if we manage to overcome this barrier, then it's all benefit to add new pairs because the energy of the system will continuously decrease. So it's important to notice that this critical size, where we have this extremum of the work of formation, is defined, of course, by the zero of the derivative of the work of formation, which means that in this approach, the chemical potential is equal to the derivative of the edge energy with respect to the number of pairs. So these two terms are equal there. And it's an unstable equilibrium because if I add more pairs, then I will continuously decrease the energy of the system. Now, this barrier scales as the square of the edge energy divided by the chemical potential, and the nucleation probability is something which is thermally activated with this energy barrier. Now, subcritical islands form and redissolve, but if an island has by chance reached this critical size, then we expect this supercritical island to grow fast because any atom will decrease the energy of the system. Now, chemical potential is important. So here are two calculations of the chemical potential, the difference of chemical potential for a 3-5 pair between a liquid and a solid. On the left, you have the case of gold-catalyzed nanowires. On the right, the case of self-catalyzed nanowire, where we have no gold. The liquid is a binary gallium arsenic liquid. And in both cases, this is as a function of the concentration of arsenic in the liquid. And you see that very small concentration of arsenic, a few percent, are enough to ensure large values of this difference of chemical potentials. And actually, we are sure that the concentration of group 5 or arsenic in the case of gallium arsenide is very low in the liquid. We don't need more. And anyway, arsenic and group 5 in general are very volatile species, so you cannot accumulate a lot in the liquid. Because the number of group 5 is very small with respect to the number of group 3, the concentration is more or less proportional to the number of group 5 atoms, number of arsenic atoms. So in the following, I will speak indifferently of the number of arsenic atoms in the liquid or the atomic concentration of arsenic in the liquid, which is very small with respect to 1, because the two are more or less proportional. And one thing which is useful to remember is that this difference of chemical potential is in very good approximation scales as the logarithm of the group 5 concentration. Now, this brought us at the idea we had about 10 years ago about the formation of individual monolayer. It starts with nucleation of a 2D nucleus. And then, because we have overcome this nucleation barrier, then we expected the formation and the completion of the monolayer to be very fast, simply using the arsenic atoms which were stored in the droplet. Then, after we have done this, we expected also that we had to wait for some time because the droplet has to be refilled, and then we might have another nucleation event and another monolayer forming. Now, if we look here, schematically at the variation of the number of arsenic atoms in the liquid or the arsenic concentration, again, they are proportional. So it increases up to a point, down pointing arrow here, where we have a nucleation. And then we expect it very fast and in this limit instantaneously to form a full gallium arsenide monolayer, which means that we deplete the liquid of the equivalent of 1 monolayer of arsenic. So we're down there. Then the external fluxes refill the droplet, so the concentration of arsenic starts re-increasing. And then at another value, because it's a random phenomenon, we nucleate another layer. Again, we consume a full monolayer of arsenic from the liquid to form a full monolayer, and then we have refilled. So that was the picture we had. Now, at this time, we did some experiments, and at this time that was by TEM, but it was ex situ after growth. So during growth, we introduced the growth of 5 nanowire, we introduced marker layers of another material at equal time intervals. And then we could measure the length of nanowire grown between 2 of these markers. And we could then count the number of monolayers grown in successive equal intervals of time. And what we obtained was this gray histogram. Now, if we assume that the nucleation events that give rise to each monolayer are independent of each other, then you all know that what we expect is a Poissonian distribution. Poissonian distribution equivalent is the blue curve here, and it's quite obvious that the experimental histogram is much narrower than the Poisson distribution. So this told us immediately that the nucleation events giving rise to each monolayer were not independent, and in fact that they were anti-correlated. And this we could understand easily using these schematics here, because when we nucleate one monolayer, if the monolayer forms entirely very fast, we deplete the liquid very fast of one monolayer of arsenic. So the concentration of arsenic decreases after nucleation and monolayer formation, which means that the chemical potential decreases as well, which means that the nucleation probability decreases as well, which means that just after formation of one monolayer, the nucleation probability is less than just before. So then we have this anti-correlation. The nucleation is less likely after the formation of a monolayer than just before. So we have this anti-correlation of nucleation events correlated with the cyclic depletion in arsenic of the droplet. And this we call nucleation anti-bunching. Nucleation tend to evitate each other. So that was the view 10 years ago. That has interesting consequences because nucleation is still random. So the number of monolayers that we go in successive equal intervals fluctuates. So there is an average, but there's also a standard deviation. If the process was Poissonian, you all know that the standard deviation would increase as the square root of the average number of events into these sequences. But what we observed and what we could calculate was in fact something which saturates very quickly at a value which is much lower than the Poisson value. And this could be reproduced by calculation, numerical and analytical. Here is an analytical calculation. And all these curves depend on various values of this gamma parameter, which is the key parameter of the theory. This gamma is simply the ratio of the nucleation probabilities after and before nucleation, formation of one monolayer. In the case of the Poisson distribution, then there is no correlation. So it's the only case where gamma equals 1. But in all cases where this nucleation anti-bunching, then gamma is less than 1. And the smaller is gamma, the lower is the plateau at which this standard deviation saturates. This has also positive consequences for ensembles of nanowires, which I'm not going to discuss today. Obviously, this phenomenon of nucleation anti-bunching is related to the low group 5 content in the liquid. However, in this first approach of 10 years ago, we assumed that there was always enough arsenic atoms at nucleation in the droplet to grow very fast a single monolayer. And the question arose, is this always the case? And the second question related is, of course, here we get small values of the standard deviations, but if this gamma is not very small, then it can be 2 monolayers, which is still fairly large. Can we reduce this standard deviation of the distribution of the length of the segment even further? Then a few years ago came the NanoMax equipment, which is a special microscope installed in a lab not very far from ours. So this is a modified environmental transmission electron microscope, where my colleagues initially fitted 2 MBE sources outside the microscope. So if we look at the heart of the microscope, the objective pole pieces, we have the electrons which come from the top as usual, but we have also 2 collimators which bring group 3 and group 5 atoms in this area where growth will take place, and we can observe the growth. And MBE in this microscope is very clean. You can observe on the specimen holder this oval here, which is a trace of one of the molecular beams. So you see that the molecular beam goes only to the specimen holder and does not degrade the environment, does not deposit atoms on the environment of the microscope. But now, of course, we have in this microscope also CVD techniques, which are not as clean, but MBE is very clean. Now, what do we see in NanoMax? So this is a view of a gallium arsenide nanowire wurtzite. So in the case of wurtzite, I'm not going to speak about this today, but the interface between the solid and the liquid is flat. And you see monolayers which are added at the interface between the nanowire, which is already formed, and the liquid. So here you see them. So what is clear from this is that never two monolayers growing at the same time. Now, to get a better view, you have to tilt this nanowire so that the interface between the solid and the liquid projects as a surface. And of course, the contrast is very weak, but then you can see a kind of white shadow which is passing across this interface. This is a monolayer growing. And from this, it's very clear that we're in the mononuclear regime. Once the monolayer has started growing, then the full monolayer will grow from this nucleus, from this initial island. There will not be another, at least in these growth conditions, another monolayer which nucleates and which will meet the initial monolayer. So we have these two important facts that confirm our basic views of about the formation of monolayers in nanowires. However, it's quite clear from videos such as these, you can see the monolayers propagating across the interface. So our old picture that the formation of a monolayer can be considered as instantaneous is clearly not valid, at least in these small nanowires. There might be instances where it's valid, but in the case that we are observing here, it's not valid because the formation of a monolayer, the propagation of a monolayer across the interface takes some time. So the picture we had before has to be revised. So let us be more precise. So here is a video from Federico Pancha. Again, we have a tilted interface, wurtzite, gallium arsenide nanowire. You see maybe a bit more clearly the monolayers forming and propagating at the interface. And on the right here, we have plotted the variation with time of the coverage of the interface by the monolayer. So the coverage varies between 0 and 1. It is 0. At some point here, we have nucleation, but very fast the coverage increases. It increases abruptly, but it does not increase to 1 as in our previous model. It increases to a value less than 1. Here it's about 0.2. So here we don't have sufficient time resolution to see what happens. So for us, it's instantaneous. Instantaneously, we form a partial monolayer. And then the progression of the monolayer is much lower. The rate of progression is much lower. And finally, we get to a coverage of 1. And very importantly, nothing happens for some time. So the coverage remains equal to 0 for some time, which for us is the sign of nucleation. Then we have to wait for some time to have a new nucleation. So we don't have two stages as believed initially in the formation of each monolayer, which would be nucleation and formation of a full monolayer followed by waiting time. In fact, we have 3 stages. We have nucleation and very fast formation of a partial monolayer. The second stage that we can observe here is the step flow. So today I will call this the propagation time, P in red. And once the layer is propagated and completed, we have a waiting time here in blue, W. So 3 stages: nucleation, partial monolayer formation, propagation of the partial monolayer until completion, and waiting time where apparently nothing happens except that the vapor fluxes refill the droplet. So these are the 3 stages: nucleation, fractional monolayer, fast, completion of a monolayer and refill of the droplet, stage 2, slow, waiting time, stage 3, and then we start the cycle again. Now let us look again what it schematically, what it means in terms of concentration. So at the bottom here, I reproduce schematically what we have measured. So stage 1, partial monolayer, stage 2, slower rate of progression of the monolayer until completion, stage 3, waiting time where nothing happens. So it's easy to understand this if we look now at the liquid. So at some point, some concentration of arsenic in the liquid, we have nucleation of a new monolayer, but we have not enough arsenic atoms or group 5 atoms in the liquid to complete a full monolayer. So our liquid gives to the solid everything it has to give, all the atoms of arsenic it can give, but this is not enough to build a full monolayer. So the concentration of arsenic in the liquid decreases, but by one monolayer. And when does it stop? So we could say we entirely empty the liquid from arsenic atoms, but this is not very, very reasonable. More likely we will reach some equilibrium between liquid and solid. So this I will consider later. So for the moment, I have a question mark. What happens after will also be studied. Then finally, the monolayer is completed, and then the liquid can refill, so the concentration will increase slowly, maybe linearly. So these stages I will study now. So let us look at the stage 1 without refill. So today I will assume that it's instantaneous. So again, I plot here on the left the reference condition for bulk phases. So we have the work of formation, the decrease of energy, free energy of the system when I form a nucleus with I pairs from the liquid. So that's exactly what I said before. And if we plot these quantities, we remember that the critical size corresponds to the equality of the derivatives of these two terms with respect to size. So it's exactly when delta mu, the chemical potential, which in both systems will be assumed to be constant, when delta mu equals the derivative of the energy of the edge of the island that I create with respect to size. So here I plot these two terms. Delta mu is constant as a function of coverage, so as a function of atoms transferred from the liquid to the solid. But we know that this edge energy varies as a first approximation as a square root. So here in blue, we have the derivative of the square root. And of course, the critical size is when the derivative of the square root becomes less than the chemical potential. So they become equal. Here we have unstable equilibrium. And after, this derivative is less than the chemical potential. So that's simply the translation that adding an atom to the island will be interesting in terms of energy. And correlatively, the work of formation itself, it increases, it has a maximum, and then it decreases. That's what we have seen before. So what about if we have a nano-sized monolayer phase as a nanowire? Then we can still calculate this derivative. And I'm not going into details, but the fact that we have the depletion of the liquid in arsenic atom that I've mentioned means that the chemical potential will not stay constant, but as I increase coverage, in other words, as I remove atoms from the liquid to the solid without refilling, because we're in the stage 1, which goes very fast, then the chemical potential will decrease and decrease logarithmically with the coverage. But here it's only schematic. So we still have normally a first intersection of the delta mu curve and the derivative of the edge energy, which for the moment I assume to be the same as in the bulk case. This is again our critical size. But because this decreases and the log will decrease to -infinity, there must be a second point where we'll have another intersection. So at this other intersection, the two derivatives of the two energy terms will again be equal. So we will have again an equilibrium. But this time, if we look at the curve of the total change of free energy, instead of an unstable equilibrium here, we'll have a stable equilibrium here. There are two things to notice. First, that this stable equilibrium occurs at a coverage or number of atoms in the island, which is less than the one which would ensure equilibrium between the liquid and the bulk solid, which would be here. That is less. So actually, we have an equilibrium between the liquid, depleted liquid, and the monolayer, the edge of the monolayer, not between the depleted liquid and the bulk crystal. And the second thing, of course, is that if we start by chance from a higher content of arsenic in the liquid, that's the orange curve, it might be that, yes, chemical potential will decrease due to depletion, but it will not cross the derivative of the edge energy before we complete the monolayer, coverage equal 1, in which case we won't get this equilibrium. So what happens here? So here we expect actually the growth to stop because we have a stable equilibrium. Of course, this does not take into account the refilling by the fluxes, but at this stage it's legitimate because it's very fast. So this we call between us the stopping effect. We might reach this. And this is something which has been, of course, studied for a long time in the theoretically in the field of, say, nucleation theory in small systems. But of course, there is very few experimental verifications. So that's what our experiments and NanoWAs allow us to do. And also it had not been considered in the field of NanoWAs. So again, it's Professor Dubrovsky in 2017 who thought about considering such phenomenon in NanoWAs, and that's this stopping effect. Now, things are more complicated. We have seen that in small droplets, we have depletion of the droplet as the monolayer grows, depletion in group 5, the rare element. But our in situ experiments allowed us also to observe the shape of the monolayer as it propagates and completes. So the gray here is the monolayer. So this is quite complicated and it's quite tricky to observe. But I go to the result. The monolayer is restrained to the hexagonal top facet of the nanowire. Here we have a top view. And complicating thing is that it's made of several segments which have different energy, segments in the liquid and segment at the triple phase line of the nanowire at the edge of the facet. And the result of all this is that here the energy of the edge of the monolayer as a function of monolayer coverage, so size of the island, does not increase as the square root, as would be the case in a monolayer which would extend infinitely. Actually, it increases non-monotonically. At the beginning, it looks very much like the square root, but then we reach a maximum, and then the energy starts decreasing until the monolayer completes. So that's a consequence of these various segments and their various energies. So very important, we have a non-monotonous step energy as a function of the monolayer size. And it's important because you remember we're interested not mainly in the step energy, but in the derivative of the step energy. So for local here is the derivative which is plotted. So the curve in black is the standard curve without taking into account this non-monotony. So the derivative is infinite at the beginning and then slowly goes to 0, as in the inverse of a square root. But if it's non-monotonous, it's also infinite plus infinity at small coverages, but then the derivative goes to 0 at some size, and then it goes to minus infinity for large coverages. So that's really important. So how can we take it into account? So let's now take into account liquid depletion when we grow the monolayer, so decrease of the chemical potential as before, the red curve. And now let us consider the non-monotonous step energy. So at the beginning, we have something which looked like what we had before. So the derivative is positive and large, but at some point the derivative will cancel and will go to minus infinity there. So before we had nucleation, this intersection between the two curves, which is still there, but we had the second intersections at the stopping size, where again the delta mu of the depleted liquid was getting equal to the derivative of the energy of the step. And now it may happen because in this part of the coverage, the step energy will decrease very fast, that we don't have this second intersection. In other words, the stopping size may be suppressed in this case. Well, all right. Interesting consequence of this is because there is nothing to stop growth, actually, the liquid can go below equilibrium with the solid phase, which would be this dash curve. And if you want to understand this, it's simply that because the step energy decreases now with the number of atoms we add to the step, then it becomes interesting to add atoms, not only because of the chemical potential effect, but also it's interesting because it increases the surface of the step, it decreases the total step energy. So we can go deplete the liquid below equilibrium. But for this to happen, it requires relatively large step energy for, of course, for the effect of the step to be important. So before there were schematic curves, now let us see what it means in the case of self-catalyzed growth. So here what I've plotted, so the dashed curves are the step energy. So the orange one is the energy in the bulk case, so square root energy, so the derivative is the inverse of the square root. And the other dash curves are in the case of non-monotonous step energy. So the black one is for a fairly low step energy, and the violet one is for a larger step energy. So what we will want to see is the intersection of these curves, which again are the curves of the derivative of the step energy, with the curves which are the other ones, the full curves that describe the variation of the chemical potential as coverage increases. So as depletion, as the droplet gets more and more depleted during this stage one. And each curve corresponds to a certain content of arsenic in terms of monolayers at nucleation. So we go from low contents, half a monolayer, to large content, 1.5. So for low content, we have our standard picture. Say we have first here, first intersection, so it's a critical size, and then we have a stopping size. If we increase the content, we can still have a stopping size. And here we see that for 3 possibilities for the step energy, we have a stopping size. It's still the case here. Of course, we have a large, very large content, then we don't get a stopping size. We're in the case where the chemical potential will not intersect the derivative of the step energy before the monolayer is completed. So here we grow a full monolayer, nothing new. But we can have cases, so this is this 1.5 here, where if we take the standard bulk energy of the monolayer, we have an intersection. But if we have a large non-monotonous step energy, the violet curve here, we don't have any intersection anymore. So in this case, we could say that the stopping effect that we would have expected with the increasing step energy is suppressed in the case of the non-monotonous step energy. But you see that maybe it's not such an important fact, because it only occurs, at least in the self-catalyzed gallium arsenide nanowires for the size that I've chosen, in a narrow window of the initial concentration of arsenic in the liquid. So it's possible, but maybe not that important. So a word of caution. So stage one was treated as fast and nearly as instantaneous, so no kinetics were considered. Now I will speak about stage two, so monolayer propagation after the fast initial growth, which is slow. But here today, I will only consider thermodynamics, still no kinetics. So in other words, I will calculate the energy of the system for a given configuration during this stage two. And I will say that the system goes to the configuration of lowest energy. So it's a kind of quasi-static approach where the system can adapt at any time to its lowest energy state. Of course, we should do a kinetic treatment. For a simplified kinetic treatment, simplified in means that there we did not consider all the features, the non-monotonous decrease of the step energy, but we treated stages 1 and 2 kinetically. Then I refer you to the last section of the paper I published with Professor Dobrowski. No, it's not 2021, it's 2020. It's a fruit of COVID. So stage two now. Stage two, so if you remember, we have propagation of the monolayer, but we have also refill of the droplet from the vapor, because this one is definitely not instantaneous. So we input from the vapor new arsenic atoms. Of course, some will dissolve, but some will stay in the droplet. And of course, the question which arises now is, from the new atoms that I put in the droplet, some might want to stay in the liquid to enrich the liquid, and some might want to join the monolayer to ensure the propagation of the monolayer. So the big question is, what is the partition of the new atoms between liquid and monolayer? And as I said, I will find the solution to this problem by minimizing the total energy of the system at a given refill. So I will imagine that I have put a certain number of extra atoms in the liquid, and I will calculate the energy of the system as a function of the fraction which stays in the liquid and the fraction which goes to enlarge the monolayer. And the lowest energy for me will be the state that the system adopts. So again, this quasi-static approach. So I don't give you the details of the calculations, but I show you the results. So the panels here are for relative large edge energy of the monolayer. So at the bottom, we look at the coverage, so what happens in the solid, at a low temperature in blue, at a higher temperature in red. So at a low temperature, you see that you have the initial growth from what was, so here I must say that I chose arbitrarily the content of the droplet at nucleation. So we form a monolayer, and then the coverage grows more or less linearly. At higher temperature, it's also the case, except at the end, the coverage accelerates. So what does it mean? If we look at the liquid now, low temperature, so I imagine that I had 0.3 monolayer of arsenic in the liquid. So I deplete the liquid, I use this, and you see that after this, it looks like a plateau. And this plateau in the liquid is very close to the arsenic concentration, which is the concentration of equilibrium of the liquid with the bulk gallium arsenide solid, which here is marked by this small bar here. So very simple picture. I deplete the liquid down to equilibrium more or less with the solid bulk solid gallium arsenide, and then during propagation, so this is the phase of propagation of the monolayer up to coverage equal 1, then I stay somewhere very close to equilibrium with bulk solid. If I'm higher temperature, then things may be different. So I deplete, but I don't deplete to the value at bulk equilibrium. And then you see that the concentration in the liquid keeps decreasing. So it does not stay at equilibrium with the bulk solid. It is something which decreases, and it decreases very fast at the end, below the equilibrium with the solid, which is another instance of the phenomenon we have seen before. So here we have something which is more complicated. But this is related to the fairly large energy of the monolayer. If I go now to a lower energy of the monolayer, then whether I'm at low or high temperature, then things are fairly ideal. So fast growth of a partial monolayer and then linear increase of the coverage, maybe except at the very end. And in the liquid, then I deplete to equilibrium with the solid, and I stay at equilibrium with the liquid during the whole propagation stage, completion of the monolayer. And in higher temperature, it's more or less the case. Maybe you see a small decrease and a small acceleration again, but basically during the whole phase of propagation, stage of propagation of the monolayer, you stay at equilibrium. So when do we expect this three-stage regime to occur? So now I come back to consider very simple considerations of size. So we may expect that the number of arsenic atoms at nucleation scales with the volume of the droplet, R3 if R to the third power, if R is the radius of the nanowire, times a kind of characteristic concentration where we have nucleation. So this will vary, but that's a kind of concentration. From this, we want to form a monolayer. And in this monolayer, of course, the number of arsenic atoms scales as the square of the radius. So we expect to be in this three-stage regime where we do not have enough arsenic atoms in the liquid at nucleation to form a full monolayers, when the ratio of these numbers is less than 1. So the ratio scales as the product of this characteristic concentration and R, the radius of the nanowires, which means that we expect to see it for small nanowire radii and for small concentrations, which probably means low growth rates. And actually, I must say that up to now in Nanomax 4 Wurtzite monolayers, we only observed this three-stage regime. In other words, we never observed up to now the regime that we studied 10 years ago, where we could form instantaneously a full monolayer. So this tends to mean that we never have enough arsenic atoms in the liquid at nucleation to form a full monolayer. In my view, this means that we study fairly narrow nanowires in Nanomax to see what happens, and also at fairly low growth rates, also because of our camera. I still strongly believe that we should observe, if we go to larger nanowires, the whole regime where we go instantaneously or quasi-instantaneously a full a full monolayer. But I must admit that this has not been observed in NanoWar. And of course, we can imagine mixed regimes where, because of the conditions, then for some monolayers, we wouldn't have enough arsenic to grow a full monolayer. And sometimes we would nucleate when we have enough arsenic, so we would have this mixed regime. So I very much would like my colleagues to observe it in Nanomax, but this has not been observed up to now. So now I suppose I have only 2 minutes to speak about statistics. So I will do it very, very briefly. I mean, I spoke about this in other instances. So going beyond monolayers, because of Nanomax, we can observe monolayer sequences. So we can start having statistics of these characteristic times. So the propagation time of the monolayer and the waiting time between monolayers. And we can get experimental histograms. And a very important quantity also is the monolayer cycle. So between monolayer completions, which are here, we have this tau-c time. So we have this experimental histogram. So there are average values if the growth conditions are stable, but because it's still random, we have a certain width to the distribution of these characteristic times. And we have this at 3 temperatures. So these are the variation of the average position of these characteristic times and the standard deviation. And basically what you see is that the averages increases if the growth temperature increases, which is nothing else than first approximation due to the desorption of the group 5. So temperature increases, there is more desorption, so it takes longer to grow monolayers. However, sometimes increases much faster than others. And in particular, the propagation time increases very slowly, whereas the waiting time increases much more sharply. So this can be, I'm not going to go into the detail, this can be modeled numerically and analytically. And briefly, we have 3 regimes. At low temperature, so I look here at the liquid. So for a low edge energy, so I'm at equilibrium with the solid. Liquid is at equilibrium with the solid during the waiting times. Then liquid concentration increases linearly up to nucleation. At nucleation, we form a partial monolayer. And then it stays at equilibrium during propagation. Then when monolayer is completed, it increases again, new nucleation, and you see that nucleation can happen at various concentration. If we increase the temperature, we have this non-linearity, which is a sign of the desorption. And at higher temperature, we have desorption and we can reach some kind of equilibrium. I'm not going to speak about this today. Now we can do this numerical and analytical calculations. So these are calculations, and you see that the numerical calculations, so these are the histograms here, are very well reproduced by our analytical calculations, which are the curves. So here it's for the propagation time, the waiting time, and the time between nucleation. But you see that what the calculation tell us is that tau-c, which is the time between completion of monolayer, should be very narrowly distributed at low temperature when we have no desorption of group 5 from the liquid. So this should be very narrow. Of course, the peak should be higher, but this should be very, very narrow. So how can we understand this? Very simply. So we assume we have no nucleation. So during the waiting time before nucleation, the concentration in the liquid increases linearly. At some point, we have nucleation. And in the liquid, we'll have a certain quantity of arsenic atoms. And our simple picture is that we use part of this to form a monolayer. In other words, the fraction of monolayer we're going to form at nucleation, very fast, stage 1, depends on the waiting time before, because it depends on the number of arsenic atoms we will have accumulated in the layer. But because the growth time after, the propagation time, I should say, is the time to complete the layer, so it's the complement of the fraction that we will have grown very fast as stage 1, we expect this propagation time here to be the complement of the waiting time before. And actually, if you look at more, what you expect in this simple picture without desorption is that tau-c, W plus the following propagation time is constant. This is why we have a distribution of the propagation time, a distribution of the waiting times, but there is this kind of compensation here, which in the end, in the calculation, produces a very narrowly peaked time between completion of the monolayers because W plus G plus P is constant. Now, it's very difficult. I spent a long time trying to fit all experiments with the model that I developed. And very briefly, there are complicating factors. So I start from the nucleation rate, where basically we have two parameters, the prefactor and the edge energy of the nucleus. So these are a priori unknown. Complicating fact is that the prefactor is temperature dependent, but very annoyingly, we measure we have a temperature, a nominal temperature for the experiments in the nanomax, but I convinced myself that this nominal temperature is much lower than the actual temperature. Not going to go into details, but we don't know actually the temperature. So each temperature at which we perform an experiment is actually an extra fit parameter. So we have many fit parameters. And the other complicating factor is that Nanomax camera, of course, has a limited speed, and the data that I present here were acquired with 4 frames per second. So the game would be to try to reproduce all our experimental histograms with a single set of parameters for the nucleation rate. So I show you at the moment the best that I obtained. So the full histograms here are the experiments, and the histograms with stripes here are the calculations. So at medium temperature, it's not perfect, but it's not too bad. Well, you would say that maybe the width of the propagation time calculated is a bit too narrow with respect to the one we observed, but there is no great catastrophe. What is annoying is that if we go at low temperature, then, if you remember in the calculation with infinite time resolution, we expected the distribution of the tau c time, the time between completion of monolayers, to be very narrowly distributed. Now, if I do the calculations to mimic the Nanomax conditions, so with especially a finite frame rate for a camera, this is somewhat broader. So the calculated histogram with the stripe is broader than one single channel. However, it is still somewhat narrower than the experimental histogram. So the conclusion, which is slightly sad at the moment, but it gives us a margin of progress, is that the quasi-deterministic regime that we predicted from the model, the fact that tau c should be very narrow distributed, this has not yet been observed. And part of this is related to the limited time resolution of the camera. So if we go to a high-speed camera that we have now, then things might get better, but it's still not clear if there is an intrinsic, some fluctuations in the system that we have not considered that would broaden intrinsically this distribution or not. And it's very important because if you manage to get into this very narrow tau c regime, then you have quasi-deterministic growth. You can say that even if you go to a standard growth equipment, you can say that I know the growth conditions, ideally, then I grow in a certain time, and I'm sure that this certain time I will grow exactly this number of monolayers. So this quasi-deterministic regime would be very interesting for nanoWAS, for heterogeneous structures, and so on. But at the moment, it is fair to say that we have not quite observed it. So I've not been moderated by Vladimir. Thank you, Vladimir. You'll let me go slightly beyond my time, but I'm going to conclude. So in this talk, we explored the very poor group 5 regime of VLS growth, which seems to be more common than what we expected before. We expect it to happen in nanoWAS with small radii at low growth rates. We have looked at the energetics of nucleational growth and single monolayers, and we have seen that in this small system, there are 2 important effects: depletion of the liquid droplet when you start growing of the monolayer, and decrease of the chemical potential, but also the non-monotonic variation of the monolayer head energy, which we have to take into account. And then we have gone to sequences of such monolayers, and we have compared the statistics of these sequences between experiments in nanomax and between calculations, which can be numerical and analytical. So in this case, there's modified nucleation anti-bunching, because after nucleation, the liquid goes to equilibrium, so nucleation probability is 0. And we have a kind of reset of the system. And this reset actually is the reason why we may expect quasi-deterministic growth, where the time periods between the completion of monolayers would be strictly fixed despite of the random nature of nucleation, at least at low temperature where this option does not operate. But this regime remains to be demonstrated experimentally. Thank you to you all. And thank you, Vladimir, again.
Thank you very much, Frank. So for this excellent talk, which was not only about semiconductor nanowires or very delicate in situ measurements, but also about nucleation and growth theory. And of course, there is a department of statistical physics here in St. Petersburg University where people study nucleation theory. So I want to make it clear, and how I understand it, the stopping size and the growth performance. So basically, you have explained perfectly that if the mother phase is very small, we can have the stopping size. And this has been demonstrated also experimentally, which is very nice. So then, at stopping size, the supersaturation is 0. Yeah. And then basically we can say that when it stops the fractional monolayer, then it stays at a stopping size at 0 supersaturation, roughly. And that's why it grows at the rate of refill. And if we additionally consider the H energy which becomes non-monotonic due to the boundaries, then we can even have growth at negative supersaturation. So basically, what you are saying is that we only need positive supersaturation for nucleation, but we can then grow at 0 or even negative supersaturation, which is amazing, of course. Do I understand correctly?
That's what they are saying. Yes, yes, that's the outcome of this theory. But this requires the relatively large monolayer edge energy, so that's this non-monotonous and this negative derivative of the edge energy is sensitive and is sufficient compared with the chemical potential. So actually, you have to. It becomes interesting to add new atoms to the monolayer, because then you decrease the total edge energy. But obviously, for this to be interesting for the system, this energy has to be large enough. If only we have a small edge energy, then this will not be sufficient. But I would predict that if this energy is sufficient, and for this nanowire, then it becomes possible that we deplete the liquid below equilibrium with the solid, even with the bulk solid. Yes.
Thank you. Any other questions from the audience? Yes, Alexei. Yeah.
Thank you, Professor Glass. Thank you for a very interesting talk. On slide number 10, you have shown beautiful animation on growth of a nanowire. I have noticed that there are some white, very bright spots appearing on the droplets and in the gas phase, in contrast to regular noise. And is there any physical meaning of these spots?
Sorry, let us, if we can.
I mean,
so I think that in the gas phase, I think it is noise. I mean, the gas phase, I don't expect to see the atoms in this microscope. I mean, atom detection in a transmission microscope is tricky. In a crystal, in a gas, I think it would be impossible. So I think all I mean, if you're speaking about these bright spots here, I think here, yes, I see. I think these are only noise, and maybe also the numerical treatment which was imposed to the image to reduce its size. So these images are very, very big. So no, I think this is noise. I think this is, yes, I see probably yes, these bright spots. I'm afraid it's only noise and it's nothing else. I mean, if you look at the video at a better resolution, I'm sure you do not see these. I'm sorry. I don't think. Unfortunately, there's no science behind it. So
thank you. That was the
only
question.
noise, unfortunately.
Okay, we have time for one more question.
May I ask?
Yes, Manos, yes.
Thank you, Frank, for the nice talk. So would the situation be very different for the zinc blende phase?
Yes, for the zinc blende phase, the situation is very different. Yes, it's something we've been working also with Vladimir and discussed with Jerry Tersov. The very different thing is that the interface is not flat, so the interface is truncated. And I think in this audience, we all know that this means that the monolayer grows probably by using atoms from the liquid, but also because when the monolayer forms, the truncation gets deeper, then there are atoms which are transferred from the already grown nanowire to the monolayer. So it's very different, because if this process is possible, you don't really need to wait for the refill by the external vapor phase. The system can use atoms which are already in the solid, just it prefers to transfer them from the already grown solid to the monolayer. And these atoms are available, they're there. And in fact, at the moment, even with quite a high resolution in our microscope, we could not observe the propagation of the monolayer, the cubic monolayer across the interface. It's extremely fast. And we grow them in the same conditions. So it's very likely that the number of arsenic atoms, say in the droplet, is still not sufficient to grow a full monolayer. The fact that it grows very fast is related to the fact that we can use atoms from the solid to grow the monolayer. So of course, this modifies deeply the nucleation from my point of view, but also the propagation of the monolayer. So the kinetics are very different, and they remain to be studied in detail. It's more complicated. It's more complicated because we don't have experimental data at the moment. We don't see the propagation. And because the situation is more complicated, because the monolayer is fed by the liquid and by the solid.
But the question is still the amount of atoms that you will get from the truncated planes. Will this be enough to complete the monolayer, or is it a self-regulating process?
That's probably a question which is open. I think we try to estimate the. It's very difficult to have a 3D view, but we try to estimate the number of atoms which were transferred from the truncation to the monolayer, and that's of the order of the number of atoms in the monolayer. So experimentally, at least, it seems that the process of transfer can go on until completion. And I think also so there we're going to be helped by the fact that the monolayer energy decreases non-monotonically. So it's interesting to transfer same as when the transfer occurs from the liquid to the solid. Then I think it will be the same. So I cannot give you a perfectly 100% answer, but at least from the elements that we have. From the experiments, the rough estimates, and from what we started modeling, I believe that this can be enough to ensure the growth of a full monolayer.
Okay, thank you.
Of course, maybe it has to be qualified depending on the growth conditions, and so this has to be studied in more detail.
Okay, thank you.
Okay, so let's thank Frank again. Thank you very much.
And my apologies for being
so
too long.
The next speaker is Jonas Johansson from Lund University, with a talk entitled Understanding Zinc Doping of VLS-grown gallium arsenide nanowires. Please, Jonas.
Thank you very much. Yeah, so thank you very much for inviting me to present here at this conference. Thank you, Vladimir. So I am Jonas Johansson from Lund University, and I will be talking about zinc doping of VLS-grown gallium arsenide nanowires. So the outline of my talk is as follows. So I will start to mention a little bit about VLS growth of nanowires, and then I will talk about aerotaxy growth, because that is the method that we have used here. So I will discuss some features of aerotaxy and also a little bit of aerotaxy modeling. Then I will come to the dopant incorporation model and some results of zinc doping of these gallium arsenide nanowires, and the results first of the model calculations, and then I will compare with experiments, and then I will sum up my talk. So just to understand a little bit about vapor liquid solid growth, we have and put that into the perspective of the phase diagram. We start with the seed material. Heat that up to growth temperature so that it can alloy with the substrate. Then we continue to put in more precursor material. So we saturate the particle and then also supersaturate the particle. So there will be a thermodynamic driving force for the liquid phase to reach its equilibrium and to also nucleate nanowire material. So what about mass production of nanowires? We normally produce nanowires in batch processes such as MBE, MOVP, hydride vapor phase epitaxy, and at least in MOVP we have a cycle time of 1 to 2 hours, and the largest machines can handle a finite number of wafers, even big wafers, and the growth rate is typically 1 to 10, maybe 100 nanometers per second. So it can be difficult to cover very large surfaces. So for that we have a method for mass production. And that method is known as aerotaxy. So it's a continuous process, not requiring any substrate. So there is no crystalline substrate, and we can choose materials quite free. So we can deposit on any substrate afterwards when we collect the nanowires, or we can catch them in a colloidal solution if we want that. It works like this, that we insert our gold particles, which we make in the aerosol phase, and we size select them here in this device, which is known as a differential mobility analyzer. So we have more or less single size gold particles, and then precursor flows which are mixed, and then we heat this up in a furnace and collect the nanowires afterwards. So we can collect them like this. We can use an electric field to make them aligned like this. So the growth rate here is actually quite high. So it's 1 micrometer per second. And we see that the growth depends strongly on temperature and on growth time, of course. But if we look at growth dependence on seed particle size, it is no significant dependence. And we can get a lot of nanowires. So this is the result of 1 hour of collecting gallium arsenide wires on a filter. So we get about 1.6 milligrams. And from our observations, we see that all wires have a polycrystalline base. And this we think is that it nucleates from 1 liquid gold particle. So it has to nucleate several attempts, and then it finds 1 good growth direction. So it starts to growing, but there seems to be some attempts before taking off in one direction. The wires are always zinc blended, but with a lot of twins. Wire length is insensitive to particle diameter and precursor flows, but we can still get parasitic growth if we have too high pressures. And there is some wire length distribution. And we have experimented a little bit, and we find that this is not due to any Poissonian broadening, but it is to different time temperature histories in the reactor, this broadening. And as we saw, higher temperature gives you longer wires. So this growth rate being insensitive to pressures and particle diameter called for a new wire growth model. So I made a general mass transport model, because the usual mass transport model we have to understand MOVP growth, that is derived for the low pressure limit and for a flat surface. So I derived a new model where we can have any pressures. We can also have a saturation in pressure. And I also considered the nanowire geometry. So I consider nanowire geometry, growth and desorption, and deposition of group 3 and group 5 at the different relevant areas. I explicitly considered the 2 components, group 3 and group 5, and not only in the low pressure limit. So group 3 can deposit here and on the particle, and what is deposited here diffuses to the particle and can incorporate. Group 5 is only deposited here. That is the only contribution, and that can also desorb. And we have an incorporation area and an incorporation rate here at this interface. Since the particle is liquid, I treated diffusion through this liquid as fast. So this is not a nucleation limited model, it's just a mass transport model to understand the overall growth rate. So the growth rate is a maximum growth rate or a growth rate coefficient, like a chemisorption incorporation rate if you want, and the molecular volume of a 3-5 pair, just to get the units right, and then the surface coverages of the group 3 and the group 5 here around the growth interface, and it's these that are being modeled and plugged into this growth rate. And I don't have time to talk much in detail about the modeling. I will not set up the equations, but I will show you the results here. So the result of the growth rate looks like this. So flux of group 3 times this phi parameter, which is this, as you all know, where we have the diffusion length over the radius. And here in the denominator, plus the maximum incorporation rate, which you also have here. So let's analyze this expression in some different regimes. So what is most interesting for ordinary, say MOVP, maybe MBE growth of 3-5 nanowires, is that we have high group 5 and lower group 3. Then we have this relation. So we have the growth rate depends on flux of group 3 times this factor here, which is proportional to 1 over the diameter. So thinner wires grow quicker, as we have seen many times. Both low group 5 and group 3, this expression, we cannot derive that from this equation here. We have to take one step backwards. And then we have a square root dependence of both group 3 and group 5. And I don't think this has been observed very much. Perhaps it has been observed in 1 or 2 experiments, because I remember a paper, CB growth, was it Lucia Sorba and Sibirev did some modeling, maybe. Quite interesting. But the most relevant for these experiments, that is high group 5 and also high group 3. And then you see we are in a saturated growth regime. Growth rate depends only on temperature, because this is a rate coefficient, and the surface coverages are essentially 1. So it's saturated growth, not pressure dependent, not diameter dependent. So I think this is how we can understand the growth rate dependencies of aerotaxi growth. So I took the chance now to talk a little bit about aerotaxi growth, because these activities we will more and more decrease. So I just want to lift this one last time, perhaps, but we will see. So in the aerotaxi, we can grow ternary nanowires. We can also grow PN junctions, but you see that it is a quite inflexible system, because the more features we want to grow, then we want to add one more stage of the reactor. So in this regard, it is a quite expensive system. So here in this segment, we add diethyl zinc for p-doping, then an intrinsic region where we have only gallium arsenide, and then n-doping with tin. So this is done in the Sol Voltaics generation 4 reactor, it was called, but that company is now not existing anymore. So now I would like to move forward to take a little look at the p-doping of aerotaxi reactors using diethyl zinc. So the model system is as follows. So we have a liquid gold-based alloy here containing arsenic, gallium, zinc, and the rest is gold. Here we have the wire, the gallium arsenide wire, and we have some zinc atoms on gallium sites. Zinc prefers to take the gallium sites, and then it will be p-doping. So the chemical potentials of zinc, gallium, and arsenic in the liquid, that is something we need, and these are calculated using CalFAD from a thermodynamic database. So this should be quite realistic chemical potentials. The reference states here are calculated by density functional theory for zinc and gallium, arsenic in their solid reference states, the same reference states which are used for these total energies. So we calculate the total energies here by density functional theory. So yeah, one thing is that these energies should be in some sense compatible with these chemical potentials. So we need the formation energy of defect, of a general defect in a charge state. Are there any questions? No. So yes, we are using the Chang-Northrop formalism for defect energy formation, and then the formation energy of a defect is calculated from a total energy where we include the defect minus the total energy of the perfect crystal minus chemical potential differences plus minus the Fermi level, which is the chemical potential of the electrons. So we look at this for zinc doping in gallium arsenide, where we have zinc on a gallium site. So the formation energy of that is the total energy of that minus the total energy of the perfect gallium arsenide. And you see that we subtract the chemical potential of zinc, but we add the chemical potential of gallium. Gallium was missing here. And then we have an extra electron in the lattice, so we subtract that. This means that there is nothing left. The only thing is left is the sort of excess energy, that is the formation energy of this defect. That is the only contribution left. We have subtracted all kinds of atomic or bulk energies. Only the formation energies left. We should calculate this guy here and this total energy here for some different sizes. As many as we can, of course, but it's more and more expensive for a larger and larger supercell. Then we take these values here and fit to a relation which is linear in 1 divided by n, 1 divided by the size, and the intercept A will be our result because we'll need the formation energy in the very low concentration limit. And then we have that. So, okay, we calculate that. That is our first task. And then the zinc concentration in gallium arsenide is just given by this exponential relation here. So N is the number of available sites for this kind of doping. That is the gallium sites in this case. And then E to the power of the formation energy. Here we need the Fermi level. So we need a relation between the Fermi level and the whole concentration. And in case we have a rather low concentration of dopants, we will have the Fermi level in the band and a little bit far from the band edge. And in that case, we would have a Maxwell-Boltzmann relation here. So we would have an explicit relation. You have all seen this in semiconductor physics courses. We would have a Maxwell-Boltzmann relation between the P, whole concentration, and Fermi level. And in that case, I could plug it in here and everything would be analytically solvable. But in our case, we have really hard doping. So we have a degenerate doping. So we have the Fermi level a little bit up in the band. So unfortunately, I need this full Fermi integral. Otherwise, it would be a big error introduced. Okay, we need an equation for charge neutrality. And since I don't add any donors, I put this to 0, and I also approximate this n to 0 here, the number of excess electrons. So I have only holes. So in that case, the doping concentration is given by the zinc concentration, which I calculate here using this relation self-consistently by plugging in this. And for all calculations, I also need to check that that the chemical potential for the solid material is positive, so that we actually have growth, because without growth we wouldn't have any doping in the first place. So I will show you some of these model calculations. So the whole concentration as a function of zinc molar fraction in the liquid droplet. So here zinc and gallium is 50%, gold is 49%, and arsenic is 1%. So I tried this at different growth temperatures, and you see that when we increase the zinc concentration, the zinc doping increases steeper and steeper, and it also increases with temperature. Here I have the gallium concentration fixed, and I change the zinc concentration at the expense of the gold concentration instead, also for different temperatures. Here you see that the increase is more linear, but the trend in temperature is the same. So higher temperature, higher doping. And you also see that it's difficult to get low doping. Whatever zinc we put in, the doping concentration tend to be high. I have also tested how the arsenic concentration affects the doping concentration. So I would say not much. So I change arsenic from 0.01% up to 5%, and there is no big change. So in my evaluations later on, I stay at 1% arsenic because it doesn't matter so much anyway. Here is for self-catalyzed growth. So zinc plus gallium is 99%, and arsenic is 1% for increasing temperatures. So you see that for low temperatures, we can cover the entire range, but here at 600 degrees, there is a range here where we don't have any doping, and here where we don't have any doping. And the reason is that we cannot grow there. So if we plot the chemical potential for gallium arsenide, we see that between these zinc concentrations, the chemical potential is negative, so no growth here. But at these concentrations, we can still grow. So at this temperature, I just hit the 0 line here. So therefore, we have this apparently non-linear effects in where we can grow or not. So if we should compare with experiments now, I remind you that we have grown our gallium arsenide nanowires in aerotaxy and in the presence of diethyl zinc as a dopant. So we measure the particle composition post-growth by EDX in a high-resolution TM. We measure the doping using electrical characterization by 4 probe measurements with this kind of setup. So the nanowire is here, and here we have the 4 measuring points. And we also optically characterize doping by broadening of the photoluminescence peak. So let's compare with experiments now. So here we see the whole concentration, the peak concentration, as a function of the pressure of diethyl zinc divided by the pressure of gallium. And the inset shows the atomic fraction of gallium and zinc from the measurements. So these values here, plus 1% arsenic, will be my inputs for calculating the chemical potentials, which will lead to a doping concentration. So it's a sort of a semi-empirical calculation with no fitting parameters. I don't count the arsenic as a fitting parameter because the result will not vary much with arsenic anyway. So the electrical measurements are terribly scattered. So you see here at this concentration, and here at this concentration. The optical characterizations are a little bit better, so they go like this. But the hardest doped wires cannot be optically characterized. They are too messy and too ugly, but they could be measured electrically, and then we found this. So the calculated values argue quite well with the experiments, at least at the lower diethyl zinc concentrations, and maybe at the maximum, but here we have a stronger deviation. But still, it is very difficult to accurately calculate doping levels without any fitting parameters. So I'm quite satisfied with this anyway. So I think it's reasonable. So with that, I would like to sum up. So I have introduced aerotaxy and as a method, and how to grow nanowires using aerotaxy. And I have shown how to calculate doping concentrations for vapor, liquid, solid growth, and applied it to zinc-doped gold catalyzed gallium arsenide wires, and good, or at least reasonable, agreement with experiments. And the calculations also confirm something we saw experimentally, that it is quite difficult to reach low doping concentrations. Perhaps due to the high solubility of zinc. So as soon as we put in some zinc, we will get a lot in the particle, and then we will get also high zinc concentration in the nanowires and a high doping concentration. So thank you all.
Thank you very much, Jonas.
Thanks.
I have a question.
Yeah.
So you mentioned some cases where you couldn't grow nanowires after adding zinc. Yeah, so there were some, yeah, here, because it modifies the chemical potential difference.
Yes.
Yes, but my question is, you mentioned at the beginning this growth model where the nanowire growth rate can be either group 3 limited or group 5 limited or incorporation limited.
Yeah.
And my question is, when you add zinc for doping, can it also change the growth regime from, I mean, transport limited to incorporation limited, for instance? Do you observe that?
In general, I think it could. Mm-hmm. But in aerotaxy, I'm not so sure, because the growth is completely saturated. Mm-hmm. So we have so high pressures, so that if we change the pressures a little bit, it will not make a big difference. And if we have so high precursor flows, then I don't think we could come to a more nucleation limited situation or so. So, but in other systems, I think there could be a chance in MBE or MOVP growth at lower pressures. Mm-hmm. Yeah, why not? Why not?
Yeah, we have observed that. I mean, like 10 years ago with the raid here, where beryllium doping of indium phosphide nanowires by MBE changed the growth regime. So it became nucleation limited at high doping levels. So the nanowires were grown, you know, much shorter compared to undoped nanowires.
Yes, yeah,
I have seen that. Yeah. For beryllium, for zinc, yes. I don't know. Thank you. No. Any other questions from the audience?
May I ask a question? Jonas, do you believe that the position of the dopant with respect to the nanowire sidewalls would affect the energy of the system with the dopant? Would it be something to take into account?
Yes. This dopant incorporation model is just, I mean, it's the same that we use for bulk. So, I mean, here, no kinetics is involved, no surface energies, nothing like this. This is only incorporation. The only thing which is specific to nanowires here, if you want to, that is the chemical potentials and the mixture here, noticing that we have gold and so on. But if in a kinetic model or a nucleation model or whatever, we need surface energies, I think, yes, the dopant would influence the surface energies, definitely. And zinc also, of course, influences these chemical potentials of gallium and arsenic here. But apart from that, there is no really nanowire specific aspects here. But surface energies, it would change, absolutely.
Or if you want, may I have a question?
Yeah.
Yes. Or so, as I remember, there've been quite a lot of attempts of doping the horizontal nanowires, gallium arsenide nanowires, I mean, planar, in Illinois. And so, what they observed the oscillations of the nanowire diameter as soon as they add zinc. So, but their system is quite specific because they get a planar growth of the nanowires.
Is it selective area growth?
No, that's not a selective area growth. That's the just gold catalyzed growth of they deposit the droplets, and these droplets spreads on the gallium arsenide surface.
Such crawling.
Yeah, that's just the scrollings.
Yeah.
So in these crawlings, as I remember, they get this effect. As soon as they add zinc, they get the droplet inflation, then deflation. So they get the oscillation of the droplets, and they also get the oscillation of the zinc concentration inside the nanowire. I understand that's a bit different system, but maybe so my question, whether you observe something like that or not?
No, we have not. We have not observed that.
So it means that their effects are surface related, I guess.
Yeah.
That's interesting.
Yeah, possibly. It's interesting. Yeah, I have not seen that.
Thank you.
Thank you.
I have
Any other questions?
Yes, I have a question. Thank you very much, Jonas, for this very inspiring talk. I have a question related to aerotaxi.
Yes.
I guess in the graph tube there is a vector flow which transport, of course, the active gas, and which transports also the nanowires to the exit of the tube. So what is the residence time of the nanowires
in the system?
Yes. Yeah.
1 to 2 seconds.
Okay.
And maybe more, in the order of seconds is the residence time, and it grows about 1 micrometer per second.
Very fast, yeah.
Very, very fast growth. Still crystalline. It's quite fascinating that it grows so fast. Yes.
Okay, thank you.
Thanks.
Further questions? So I don't see any, and so let's thank Jonas Johansson again.
Thank you. Thank you very much.
Thank you, Jonas.
Thank you.
So now I think it's my turn. I will try to share the screen. Okay, so the title of my talk is Modeling MBE Growth of Nanowires on Reflecting Substrates. Here is the plan. So I will start with introduction and then discuss an analytical model for selective area growth of 3,5 nanowires by MBE on reflecting substrates, capturing the most important features of this growth.
Vladimir, we don't see your screen.
You don't see my screen?
We see your screen, but not the presentation.
No, we don't see the presentation.
See.
We see just the Finder where we see all your files.
I see. So I will try to restart. Is it better now?
Yes.
Yes, now it works.
Can you see the presentation? Okay. So now it's okay now.
Yes, perfect.
Thanks. Okay, so I will start with introduction and then I will present a model for selective area growth of 3,5 nanowires grown by MBE on masked substrates. And I will then consider kinetics of axial and radial growth in different stages and compare the results with some experimental data. So of course, we have started growing gallium arsenide nanowires with a gold catalyzed VLS process, where we just deposited a thin layer of gold and then annealed to break the film into an ensemble of droplets on gallium arsenide 111B surface, and then grew the nanowires, which were quite irregular in terms of their sizes and positions. And we always had this parasitic layer which grew between the nanowires. Yeah. And then people introduced selective area growth procedures, where they used basically surface preparation using lithography. And if we compare, like in this paper, for instance, selective area growth of gold catalyzed, in this case, indium phosphide nanowires, with the same growth under exactly identical conditions without surface preparation, so on and patterned indium phosphide surface, so we can see a clear difference. So the masked surface, the mask is silica in this case, improved the growth selectivity, while without any mask, there are parasitic structures surrounding the nanowire bases. So selective area growth has this advantage, as well as, of course, when you process the oxide or nitride layer, you can organize your nanowires in regular arrays by organizing the growth seeds. And nowadays, there are different methods of growing 3,5 nanowires by selective area approach. So you can still use gold, like in this case. These are gold catalyzed indium phosphide nanowires grown on indium phosphide substrates. Or you can grow 3,5 nanowires by self-catalyzed approach, by pre-depositing gallium into the pinholes in silicon oxide, or you can grow them without any droplets at all in the purely selective area growth approach, where the pinholes direct the nanowire growth without any droplets on top. Yeah. And in some cases, there have been publications showing that in some cases, the selective area growth and VLS growth can even coexist in one sample, depending on the size of the wire as well as growth conditions. So what is nice about self-catalyzed growth of gallium arsenide nanowires, in this case, on silicon 111 substrates with silica masks, that we can narrow the size distribution within this array of regularly positioned nanowires in terms of both diameters and lengths. So first of all, in most cases, when we use this pinholes, we increase the homogeneity, I mean, in starting times for growth compared to unprocessed substrates. And then by using appropriate growth conditions in self-catalyzed approach, we can narrow the diameter distribution, where we can start from gallium droplets that are very different in sizes, like shown here, for instance, this white histogram. And then after some time, after 5 minutes on MB growth in this case, if we measure the diameter distribution of the resultant nanowires, it appears much narrower than the initial droplets. Yeah, so we can narrow up the diameter distribution during growth, and we can also observe sub-Poissonian length distribution of gallium catalyzed gallium arsenide nanowires, like for instance in this paper, and also we published with Emmanuel Demarquis another paper. So basically the droplet preparation techniques were different, but what we see that under optimized conditions, after some time, we can observe the length distribution which is narrower than the Poissonian, which is of course amazing. And this is due to the effect of nucleation anti-bunching, as Frank explained in his talk, which results in sub-Poissonian sharpening of the length distribution. So by using this growth, we can first of all completely suppress the parasitic growth on masks, so we can have a regular position or positions predetermined, predefined position of the wires on a substrate, and we can have a narrow size distribution. But of course, there are issues with vertical yield of nanowires, for instance, and there are many others, including the growth model, which is in fact my topic for the last 15 years or so, because much less modeling works were devoted to this growth on mask surface compared to maybe growth on patterned surface. And the difference is here. So there are two possible mechanisms considered so far for the material transport of, let's say, group 3 atoms from the substrate to the wire. The first one is the usual one, is surface diffusion. So this is the case of a sticky substrate where atoms can stick and then diffuse. Of course, they can form parasitic islands, but some of them diffuse to the base of the wire and then to the top, and this process is driven by the chemical potential difference here and there, and they will contribute into the nanowire groups. The second one is the case of reflecting substrate, where no atoms can stay, so they are scattered or reflected or re-emitted from the mask, and these atoms can then also contribute into nanowire groups. Yeah. So this is the mechanism considered. There have been a few papers on modeling this re-emission. For instance, Dan Letts and Sandra Gibson-Raylepierre and Sasha Kerlich before. So most of the works considered the cosine emission law, or the Lambert scattering, without actually physical justification of this particular scattering law. On the other hand, many works, like for instance this one and the one from Israel, they did not fully consider the shadowing effect, because we all know that MBE is a directional deposition method where the direct flux as well as the reflected flux can be shadowed by the neighboring nanowires, and this process is very important. So my considerations are actually based on the paper from C2N, Fabrice Allaire and co-authors, where the authors were able to accurately measure and model the growth kinetics of self-catalyzed gallium phosphide nanoarrays by using markers, gallium arsenic phosphide markers. So what was done experimentally is MBE growth of gallium phosphide at 600 degrees for 60 minutes. So they introduced 122 markers, and this growth time at this growth rate corresponded to slightly less than 500 nanometers deposition thickness, equivalent deposition thickness. So we can relate the marker number to either time or the deposition thickness. So the beam angle of gallium was 32 degrees, and the area per nanowire in hexagonal array was this. Yeah. So the pitch of the hexagonal array was 500 nanometers. And the beta, the contact angle of the droplet, was measured constant during growth, and it equaled 135 degrees. So the axial growth was measured from the distance between the markers, and radial growth was also measured based on the radial extension of the markers, and the droplet enlargement was also monitored because the nanowire radius was monitored. So that's the measurements. And this is the graph showing the axial growth rate of an individual nanowire, which first increased almost linearly with the marker or time, and then it saturated at 1 nanometer per second. So, and the length grew from 0 to slightly more than 3 microns in 1 hour. So the diameter enlargement was quite substantial. So it grew from 40 to 140 nanometers in 1 hour, the diameter. And the droplet was extending, so swelling at a constant beta, and then in this growth, the step flow starting from the top of the wire helped maintain the almost cylindrical shape. So with a slight tapering, which we will ignore. And then what was measured, most importantly, this curve, which is the total gallium flux onto the wire, including the droplet, which started from 0, and then it reached the maximum, and maximum is the maximum flux, which is simply given by the pitch. So this is the area per nanowire in this particular array times the growth rate V. And then to feed the data, several models for the re-emission were scattered. First of all, the diffusion, surface diffusion, was ruled out because it required unrealistic time dependence of the chemical potential driving. So the conclusion was that the main contribution was the re-emission of gallium from the mask. And then it was found that the best feed could be obtained with just specular emission from the mask, rather than Lambertian scattering or random uniform angle distribution of re-emitted gallium. Meaning that gallium atoms arriving onto, impinging the mask surface, just bounce off the surface at the same angle, and then they contribute into the nanowire. So this made me, interested, and I developed some model for the, first of all, for the total group 3 influx for MBE growth on reflecting substance. So this flux, of course, is defined as the total flux which contributes into the time derivative of the nanowire volume plus the droplet volume. So the nanowires will be considered as cylinders with radius r and length L, and beta is the contact angle, and f is the known geometrical function relating the droplet volume to the radius of its base. So we consider group 3 in the model, group 3 atoms only, no growth on the mask, no re-emission from nanowire sidewalls or droplets, no desorption of group 3 atoms from nanowires or droplets. And we also consider that all nanowires in the array have the same dimensions. So then what I write is that the total flux equals direct flux plus reflected flux. So for the direct flux, we write it equals V, the growth rate at a given beam angle, times S, where S is the total area exposed to this flux. As long as S is smaller than P squared, where P is the pitch of the square array, but this doesn't matter which array. And then after S exceeds the area per nanowire, it should equal V times P squared. So this is the maximum possible flux per nanowire in MB. And of course, P squared is related to the nanowire. So then, for the reflected flux, it equals V reflected times the nanowire surface area exposed to the reflected flux. And from the total balance of gallium, we can write that V reflected equals V1 over S over P squared, provided that S over P squared is smaller than unity, or 0 when S exceeds the P squared, simply because in this case all mask is shadowed by the nanowires. So from these considerations, we have this, of course, simplified expression. So F equals V times S plus 1 minus S over P squared S prime. Or for the flux normalized to its maximum value, we have this. And this model is insensitive to the type of scattering. So now we have introduced specular scattering. And in specular scattering, of course, S is known. This is the nanowire area exposed to the direct flux. But for the nanowire area, surface area exposed to the reflected flux, we have the same contribution from the nanowire side walls because the angles here are exactly the same. But for the droplet, we have this high coefficient, which is different because the droplet surface area seen by the flux is different for the direct and scattered flux. But this can be calculated using Franck-Lens expressions given in this paper. And of course, for catalyst-free nanowires, this high prime is simply 0, and high equals cosine alpha, basically, in catalyst-free growth. So therefore, if we introduce X, like S over pi squared, so what we have is this expression. And if we ignore completely the top surface, it becomes simple. So it's 2x minus x squared. So basically what we see that at the beginning, if we ignore the top surface, we have twice the direct flux impinging the nanowire side walls. And finally, when x reaches unity, so it becomes 1. And this is how F over F max depends on the normalized surface area of the wire, basically. So it always saturates at 1 because this is the maximum. So from this condition, we can also determine or estimate the shadowing length corresponding to the complete shadowing of the mask surface by the nanowire area. And this is given by this simple expression showing that the shadowing length, of course, decreases as I increase the beam angle. It also decreases as I increase the nanowire radius, because the surface area which blocks the flux is larger. And also it, of course, increases with the pitch. So the larger is the pitch, the larger is also the shadowing length, before which the mask is open or partly open to the flux. And these graphs show the dependencies. And if, for example, I assume that in the case of gold catalyzed gallium arsenide nanowires, the diffusion length of gallium on the nanowire sidewalls limited by incorporation. And now it can only be limited by incorporation because there is no desorption taken into account. So, and this was estimated at 1.5 micron in some works, or even there were works saying that it was more than 2 microns. So these shaded zones correspond to the regions in terms of pitch and nanowire radius, initial nanowire radius, where there will be no radial growth at all. For instance, by decreasing the pitch, we can reach the regime where there is no radial growth for a given lambda, the diffusion length, or by increasing the alpha, or by increasing the radius. So comparison with the experiment, what I did, I actually computed the normalized gallium flux as a function of gallium deposition thickness and compared it to the data given in published in this nanolabs paper from C2. So basically what we see, so I used this nanowire radius as a function of gallium deposition thickness deduced from the paper and the length deduced from the paper, which first increased superlinear and then linearly with the age or the time. And then if you compare it to more advanced calculations given in the paper, where first neighbors and second neighbors and third neighbors were taken into consideration, you can see that my simple curve is not much worse. The only deviation is here, but here, the experimental flux starts to decrease, and I don't know why, because to my opinion, it should saturate at unit, So here, and also even the result calculated by Frank and Fabrice is not very accurate either. So that's the reason. So now, if we have no radial growth at all, we can describe fully analytically the evolution of nanowire lengths in such a growth on reflected substance. So this is basically the governing expression for the total volume. But if the radius is fixed, so I can immediately get the solution, which is quite interesting because it's not exponential. It contains exponential term, but it's more complex than exponential compared to what we have modeled before for MBE-grown nanowires on sticky substance. So basically what we see if we plot nanowire lengths against deposition thickness, so at a fixed radius of 50 nanometers and for a given angle of 32.5 degrees, the beam angle. So what we see that the curves increase fast in the beginning, But then after you reach the shadowing lengths at a given radius, they become linear in time or in age. And even here at the beginning, the increase is more complex than exponential. So I have then compared this with the results given in this Dan Davaso paper. So this was the observation. So this was MB, sorry, not MB, but CB growth of indium phosphide at 420 degrees. So they grew nanowires from different size droplets, let's say, and what they saw that thin nanowires were grown longer, which is also within the model. But then in one nanowire, which was not tapered, they introduced the markers in order to measure the height or the length versus growth time. And that was the exponential fit. You see? And no shadowing was taken into account. So if we take into account the shadowing effect as well as reflection, the specular reflection in my case, so the curve would fit the results much better. So there is no discrepancy at all, yeah, compared to the exponential curve, which was produced again without taking into account shadowing. So then, of course, in self-catalyzed nanowires, we see the radial extension all the time, in most cases. So we can't say that these nanowires grow at a constant diameter. So we have to consider radial growth in the intermediate stage, which means that before reaching the maximum flux, okay? So in this case, the situation becomes more complex because you have to solve two equations, actually. One is, again, a similar model for the nanowire torque, which gives you dl over dh. And the second one is derived using this from the general governing equation. So we have two equations for L and R, and they are non-linear. So, but we can, of course, solve it numerically. But what is interesting to know that in some cases, and exactly when I ignore here in dl over dh, this term, the droplet surface compared to the side walls. So I can derive this expression, which is then exact, so that the volume of the wire increases exponentially with the length of the wire, but not with time, with the length, yeah? And this should be more accurate for a catalyst-free nanowires without any droplet on top, because the contribution from the top in their case is much less. So then I compared this prediction to the results published by Hertenberger, so basically from Gregor Hobmüller, long ago. So what they did, they grew by MB indium arsenide nanowires without any droplets in square arrays of different pitches ranging from 250 to 3000 nanometers. And they measured the length, the mean length, and the diameter, which increased sublinearly with the time, growth time. But if I replot this in terms of nanowire volume versus length, so I can see that all the results, imagine the pitches are very different. There is a huge difference between 250 and 3000 nanometers pitch. But all the results within the error bars, they follow this exponential curve that was predicted. So finally, I consider what I call asymptotic stage of nanowire growth, where the growth occurs at the maximum flux, which is simply given by the surface area per nanowire in the array. So then, of course, neglecting the contribution from the top, which is exact for selective error nanowires and only approximate for the nanowires with droplets. So I have this simple. So the equation, the nanowire volume increases linearly with time, and the coefficient is given by just surface area per nanowire. But also using this dl over dh, which is our usual equation. So there is no more reflection, there is no more re-emission because the mask is blocked, it's shadowed. So I have the usual, top surface or droplet surface plus the diffusion from lambda, from the length lambda, which is the diffusion length. And then I have the boundary conditions. But what is interesting that the radius now depends on L. And therefore, for dl over dh, I now have the equation, which is actually not as simple as we thought before. It's called a Cheney equation, where dl over dh contains the contribution from the top plus epsilon times L square root of L over h, where epsilon is proportional to the lambda and inversely proportional to the pitch. And the solution of this equation is, it's non-linear, so it's not very simple. But what I can see, of course, I can plot the graphs, but what I can also see from the solution, that in the asymptotic stage where the time, let's say infinite goes down, L over H tends to a certain value which increases with epsilon. So meaning that the higher, the larger lambda, the larger is L over H, and it decreases with the pitch. So finally, the nanowires grown in the smaller pitches will become taller, which is quite impressive and interesting. And for R, the radius, so it is proportional to just the distance between the nanowires. So this would relate to coalescence or merger nanowires. So what I can see from this solution, that nanowires will never merge, provided that there is a diffusion from the sidewalls to the top, any diffusion. Even in the selective area grown nanowires category 3, where the second term is actually 1. So this is very important. Nanowires will never merge if there is a diffusion. So I can produce this length time or length age curves in the asymptotic stage. What I see that both length and radius increase sublinear, and that's what most people see in the growth kinetics of, where both axial and radial growth are included. So, and for larger pitches, of course, the radius grows much faster, while for 300 nanometer pitch, it stays constant, basically. So there is no radial growth. For larger pitch, it increases. And as a consequence, the length becomes more and more sublinear. And finally, the curves cross. So finally, the nanowire, which is grown in larger array pitch, it becomes shorter than the one grown in smaller. The final result, so in some cases, if we change this p squared to the collection area of the nanowire on the surface, so Cheney equation may apply from the very beginning. And in this case, the nanowire volume would be a linear function of time. And that's what we have seen in this paper with my friends from Germany, Theo and Uli, who did this X-ray in situ X-ray monitoring of nanowire growth using portable MBE in a Petra 3-line and synchrotron radiation, where of course it was tricky to actually restore or obtain the nanowire geometry as a function of time from the diffraction patterns, but they did that. And what they saw that was the nanowire volume here increasing linearly in time from the very beginning, while the radius of the wire, and this was gallium catalyzed gallium arsenide nanowire on silicon oxide, silicon with pinholes, so usual. So the radius stayed constant at the beginning, and then it started to increase slightly sublinearly. But the increase was so large that the length, which is given here, almost stopped growing. So in the first stage, there was a linear increase in the volume and in the length, and in the second stage, it was more radial. And this is also within the model. So finally, my conclusions is that a simplified analytic expression is given for group 3 flux impinging nanowires accounting for re-emission as well as shadowing effect in MB. An analytical formula is given for the shadowing length versus different parameters. And without radial growth, we can analytically calculate the growth kinetics, and we can see that nanowire lengths increase faster at the beginning, but not exponentially as in the earlier models, but then converging to linear time dependence after reaching Fmax, the maximum flux. Most complex is the intermediate stage, where in some time the volume of high aspect ratio nanowires increase exponentially with the length, with the only fitting parameter, which is the lambda, the diffusion length. And in the asymptotic stage, both lengths and radius increase sublinearly with time. We have obtained good fits to different experimental data. And I think the model is not specific for 3-5s and can be used for also for elemental semiconductors or in other material systems, where the major effects are the reflection from the matte surface and shadowing, which is always present in MBE. And maybe the last conclusion, that the asymptotic stage, where the surface is blocked by shadowing, is exactly the same for reflecting or sticky substrates. So it doesn't matter anymore because it's, there is no more substrate in play. I would like to thank Frank Glass, George Sillen, and Ulrich for helpful discussions and also reading their papers, of course. And I have to acknowledge research grants of St. Petersburg University and Russian Science Foundation. And I would like to thank you all for your attention. Thanks. So, yes, thank you very much.
Since you are also the chairman, you should ask for questions, I think.
Oh, yeah, of course. Yeah, please. Yes, of course. I should have done that before. So yes, please, I will be happy to answer questions if any.
May I ask a question, Vladimir?
Of course.
You mentioned that your new model, which I think will deserve further study, at least from my side, is applicable for any re-emission scheme pattern.
You mean any geometry?
I mean, whether it's specular or cosine.
Sorry, the reflection. No, well, yes and no. So
No.
this expression, can you still see the screen?
Yes.
So this expression where I do not specify the areas exposed to the flux, so S and S prime, is general.
Mm-hmm.
So I think, well, it is approximate, of course, but it should be valid for any type of relation. But once I specified the surface areas, I actually introduced them all.
All right.
So here I use specular emission based on your paper. But and then everything after that relates to the particular case of specular.
Mm-hmm.
Yes.
All right.
Because here what I introduce is that the total gallium balance and the shadowing effect. So I do not specify the reflection or emission law here. But then finally I have to introduce it. So here I use specular emission, but I can use any other, but this would change S and S prime.
Thank you.
May I have a question?
Yes.
As I get it, so this model actually can be generalized to random positioning of the nanowires if you somehow can describe the random distribution of the
yeah. This is a very interesting question. So because it is approximate, so I think it's not sensitive to
the shape of the
geometry of the array. In real life, of course, it may be sensitive, but it depends also whether I think we rotate the substrate or not. So because the only parameter which enters my equation is this pi squared, which is the inverse of surface density.
Which could be
so
randomized.
There is no dependence of the particular geometry of the array, whether it is square or hexagonal or anything else, or even random. So there is no difference here because it's simple. The only thing which actually enters the equation is the surface area per nanometer. So I can equivalently present it in terms of just nanowires.
Okay.
Because it's simple.
That's interesting to try actually.
Yeah, of course.
Thank you.
May I ask another question?
Yes.
In the end, you managed to reproduce many different sets of experimental results. And as I understand it, you do not take into account any re-emission from the sidewalls of the nanowires. Is it right?
No, it's here. No re-emission from nanowire sidewalls or droplets.
So
only from the mask.
why do you think that the results are so good at the end without considering re-emission from sidewalls? Is the conclusion that it's negligible or something else?
Well,
why is it so good without taking into account this?
Well, I think because it's gallium arsenide, so I think it's a sticky surface. So so I do not consider that, at least, and I maybe I'm mistaken, but I don't think you have considered it in your paper. No, I think it was only emission from the mask.
Must admit, I don't remember in this particular case.
Well, at least in my model, there is no re-emission from nanowire sidewalls, which is taken into account. Hence, no material exchange between the wires, like in subfeld and Pagander. So I don't consider that. So the process that I imagine is that there is a reflection here, and then when it impinges the sidewalls, it sticks and then it diffuses. And since there is no desorption, so it contributes into either axial or radial.
All right.
Of course, this is an assumption. Okay, so I have waited for some time. I think we did quite good regarding time, so we are only 15 minutes behind the schedule, but it doesn't matter because now we have the break, and we will resume at 2 o'clock according to the schedule. But the link will be open at 1:30. Okay, so you can reconnect. The same Zoom link. Are there any questions? I mean, not regarding my talk, but for the future, next session or anything else. No questions? Okay, so I will see you all in 1 hour and a half at 2 o'clock. Thank you very much.
See you. Thank you.
Thank you.